And welcome to the final video on calculating enthalpy change. This one is looking at using experimentally gained data, usually through a process known as calorimetry, to calculate the enthalpy change in a given reaction. So what I'm going to do here today is first off I'm going to talk about a concept called the specific heat capacity of water, and then we're going to look at how that is used to calculate and measure the enthalpy change in a reaction. Okay, so the most important thing when you're measuring the enthalpy change is that a reaction will either give out or take in heat to the surroundings. So if we measure the temperature change in the surroundings, that gives us an understanding of what's actually happening within the system. But we need to carry this reaction out in a closed system so that no heat can escape. Because as soon as heat escapes, that's going to change our results. Now this works really easily if our reaction happens in an aqueous solution, because we can measure the temperature change of the water directly as long as we keep things insulated. If it was something like a combustion reaction, then it needs to again be in a closed system and we need some way of measuring that temperature change and like what substance is actually absorbing that heat. Okay, so mostly we talk about this in respect to water, and we use a concept. Water has a concept called specific heat capacity. Well, all substances do, but water's most commonly used. So the specific heat capacity is the amount of energy required to raise the temperature of that substance by 1 gram. 1 gram of that substance by 1 degree. So in water, if we have 1 gram of water, how much energy does it take to raise the temperature of 1 gram of water by 1 degree? And we know quite clearly that this is 4.18 joules per gram of water per degree C. And this is a standard piece of information that we can look up. So if we have different amounts of water, if we want to raise its temperature by different amounts again, we can easily calculate how much energy we have to put in. And of course, on the flip side of that, if we know how much the temperature of water has increased, and how much water we have, we can work out how much energy has been required to do that. Okay, so we use an equation, which is shown here, called Q equals MC delta T. Now you don't need to memorize this, you get given this in your data sheet in the exam, where Q is the energy change. It is the amount of energy being transferred to or from the water. M is the mass of water, which you can calculate directly from its volume because water has a density of 1, therefore the mass of 1 gram of water, the mass of 1 mil of water is 1 gram. C is the specific heat capacity, which you always get given, and delta T is the temperature change. And as for any change in quantity, it's always the final temperature minus the initial temperature. That means if the temperature has dropped, it's going to be a negative number, just to be aware of that. Okay, so that helps us calculate how much energy has been gained or lost by the water for a specific amount of reactant. To calculate the enthalpy, remember enthalpy is calculated in kilojoules per mole, we need to figure out how many moles of substance must have reacted to create that energy change. Okay, so that's the final step. So often we'll do these reactions in something called a calorimeter. Calorimeter is insulated. Often we'll do them in the laboratory simply as 2 coffee cups, one set inside another. Designed to keep heat in, put a stopper on the top, put a lid on the top as well, and a thermometer, and you can measure the temperature. And we should do some experiments like that in the laboratory just so you can see what they work like. However, in this situation, I'm purely going to focus on how to calculate this given an exam question, because I can't really demonstrate that over the computer very easily. So this is an exam question that was in the 2019 NCEA exam, and this is about calculating the enthalpy of combustion of liquid hexane. And it's done by burning a known amount of hexane, so combusting that hexane, and measuring the temperature change in a known mass of water. So basically, we're using the burning hexane to heat up some water. If we know how much hexane we've burned, and we know how much the temperature of the water changes, we can work out how much energy has been released in theory. So in this case, 5.22 grams of hexane is burned, and the temperature of 400 grams of water increases from 20.5 degrees to 36.7 degrees. So using these results, calculate an experimental value for hexane, the combustion of hexane. And you're given some data in there, particularly the specific heat capacity of water and the molar mass of the hexane. Now at NCEA levels 2 and 3, you do not get given data that you are not going to use in your question, in your calculation. So all of the data of this question is stuff that you're going to need to use. And just put that out there. Scholarship's a bit different, but at level 2 and 3, you use all the data you've been given. Okay, so to start with, we're going to take this equation, Q equals mc delta T, where Q is the amount of energy that has in effect been gained by the water. So to find that out, we need to know the mass of the water, which we're given in the question, 400 grams. The specific heat capacity of water, we're given that in the question. And the change in temperature. We're given the final and the initial temperature, so we just need to do a simple piece of math to work that out. We can then take our equation, substitute our numbers into it, and that gives us an answer. Now that answer is in joules. You know it's in joules because the specific heat capacity is the only one that has energy in it, and its unit is in joules. Now enthalpy change, as you know, is usually calculated in kilojoules, or rather kilojoules per mole, so I recommend converting to kilojoules right now. Now the interesting thing about this calculation is that Q is the amount of energy that has been gained by the water, which is the surroundings. When we calculate enthalpy change, we want to work out the amount of energy that has been lost from the reaction system. So when we come to calculate the enthalpy change, we use this formula. Delta H equals a negative Q divided by N. So we've changed the sign on our value of Q to reflect the fact that if energy is being gained by the surroundings, it's being lost by the system, or vice versa. Okay, now we obviously also need to work out N, and N is the number of moles of hexane that have been burned. So we've got the mass. In the question, we got given two masses, the mass of hexane and the mass of water. You use the mass of water to calculate the energy gained by the water. You use the mass of hexane to calculate how many moles of hexane are involved. And the formula, of course, moles equals mass divided by molar mass. And again, this one you get given to you on your data sheet. And you're given the molar mass of hexane, which is a really, really big hint that you're going to need to use this. Okay, so we've got 5.22 grams of hexane divided by a molar mass of 86.0 grams per mole, gives us a total number of moles of 0.0607. Now, I've written these answers to three significant figures, but what you should do is keep the number in your calculator. Do not clear and re-enter it. Leave it in there to like 10 significant figures. It doesn't matter. It's better than rounding too early. Please don't round too early. You'll lose marks if you round too early. Okay, so then we take our equation, delta H, which is what we're trying to work out, is equal to negative Q divided by N. Negative Q, well, Q is 27.1 kilojoules. So we're going to turn that into a negative 27.1 kilojoules divided by 0.0607 moles. And that's going to give us an answer of negative 446 kilojoules per mole. Now remember, this is a combustion reaction. So the fact that this answer is a negative enthalpy change is exactly what we would expect. So this is that reality check at the end. You sit there and you go, okay, does this answer make sense? It's a combustion reaction, so it's got to be negative. I've rounded to three significant figures. I've got a correct unit in there. Those are all things that are required for excellence. And as you can imagine, with this sort of multi-step calculation, this is an excellence question. Okay, but it has another part. So the second part of this question, and this comes up every time there is a calorimetry question, they ask the same follow-up. They say, explain why the experimental value is less negative in this case than the theoretical value, or it's usually just different, but in this case they're particularly specific. It's less negative. There's another hint there, right there, that your answer should be a negative number. Okay, so why is it different? Well, there's two things to be aware of in some. First one, a diagram was actually provided. This is the diagram that was provided. The second thing is the word explain. It doesn't just mean state a reason, it means explain why. Okay, so when you look at this diagram, hopefully you can see that the whole system is open to the air. That means that when the hexane is burning, not all the heat is, some of the heat is going to be lost to the surroundings. It's not a closed system. Now that is stating a reason, it is not explaining why. The explanation is that some of the heat energy is going to be lost into the surroundings rather than being transferred to the water. Therefore, the temperature of the water is not going to increase to its maximum amount, and therefore the result will be too low, basically. Okay, the amount of enthalpy change will be too low for this actual reaction. And you'll notice, actually, there's a really big difference between negative 446 and negative 4163. That's like nearly 10 times difference. Okay, so it comes back to, it's not happening at standard conditions. So you don't know whether the temperature or the pressure of the surroundings may have an impact. That's likely to be less significant than the fact that it's not a closed system, and therefore the energy is being lost to the surroundings rather than being transferred to the water. That is the most important thing to put in there. But explain doesn't just mean give a reason. It means tell me why this has affected the answer. Yeah, so please be quite specific about that. Okay, so these are the sorts of calculations that you are expected to do for these calorimetry questions. They turn up probably 2 years out of 3 in NCEA, so you can probably expect to see one. And if you don't, then that's just your good luck. You get given the Q equals MC delta T calculation, but you don't get given delta H equals negative Q over N. So you need to be aware of that. The units should be a big hint for you. Okay, I hope you found this useful. Please go away and practice some of these calculations, and I will see you in the next video.